All right, kids, how we doing? It's Stats with Glenn right here. Look at that. I've done it. I've done denim on denim just for today's special lesson, kids. Okay, so we're about to enter a new phase. Chapters 1 through 5 were primarily about what we call descriptive statistics, culminating in statistical prediction, which is important and great, and as you can tell, I love it. However, it's qualitatively different than what the world we're about to get into. So we're about to get into chapter 6, which is going to be an introduction to inferential statistics. So you might recall from chapter 1, long time ago, when I introduced the basic concepts of descriptive versus inferential statistics. Inferential statistics is counterintuitive, or it's not obviously accessible and intuitive. For that reason, I have dedicated chapters 6, 7, 8, and 9 in straightforward statistics to the basic concepts of inferential statistics. Again, you'll see, because it kind of requires some abstract thinking that people aren't used to. It's kind of non-intuitive, but we're going to get there. You'll understand it, you'll appreciate it, and you'll be able to apply it to lots of practical questions by the end of the course. As you might remember, the definition of inferential statistics is essentially a series of statistics that allow you to make an inference about some pattern of data that probably generalizes to a broader population. So if I'm studying how people work in their statistics course, and let's say I did a study to see how do people do if they read the textbook versus people who do not read the textbook. And I find that people who read the textbook on average do better in terms of their scores. Inferential statistics would allow me to not only say the group who read the textbook did better, but I can probably infer that college students in general who read the textbook will do better compared with other students. So it's making that kind of inference. Inferential statistics are based on probability. So with probability, we have what we call probability distributions. You'll recall from, I'm going to say maybe chapter 2, one of the earlier chapters, where we talked about frequency distributions. A frequency distribution is a distribution of scores, and it tells you how frequent different values are. So if we had 10 people take a test and 3 people got an 85, that value of 85 would have a frequency of 3, because 3 people got that. Frequency distributions correspond to actual data. A probability distribution corresponds to a mathematical function. So a frequency distribution corresponds to actual data, but a probability distribution is mathematically generated. So a probability distribution is mathematically generated, and it's used in our field for inferential statistics. There are a few famous probability distributions that are especially important in inferential statistics. But let me start by showing you how is a probability distribution generated. So how is a probability distribution generated? These things are generated mathematically based on simple mathematical processes that underlie probability. So I'll give you an example. Remember, e.g. is a Latinism simply meaning for example. So here's an example. Imagine that you had a coin and you were going to flip it on 2 occasions. So you flip a coin twice. We can determine the probability of the different potential outcomes. So what are probabilities of the different potential outcomes? So you'll see this will be a probability distribution. If we flip a coin twice, what are the probabilities of the different potential outcomes? And along the way, we'll learn some of the basic, simple rules of probability. Okay, so we're going to be moving toward a probability distribution. Probability distribution is like a frequency distribution. We have an x-axis. The x-axis are the potential values. Remember, values are potential scores for a variable. And the y-axis, if this were a frequency distribution, it would correspond to frequency. But here, it's going to correspond to probability, or p. Something that is 0 probability means it will never happen. Pigs flying, for instance, is probably a 0 probability. I'm going to put this at, I'm going to put 0.25, I'm going to put 0.5. 1.0, if something has a probability of 1.0, that means it is definitely going to happen. So we're looking at the probability of getting different outcomes associated with flipping a coin twice. Okay, so let's take a look at the number of heads in particular on 2 coin flips. How many possibilities? One possibility is 0. If I flip a coin twice, I might get tails twice. So that would be 0 heads. I could get 1 head. And I could get 2 heads. So this will be the guts of my probability distribution. Now if I were actually going to do this, I would have flip number 1 and flip number 2. So for this first possibility, of 0 heads, that would be flip number 1, I would get a tail. Possibility of getting a tail is 0.5. 50% of the time I'll get a tail. To get 0 heads on 2 flips, I not only need to get a tail on the first flip, but I also need to get a tail on the second flip. The probability of getting a tail on the second flip is independent of whatever happened on the first flip, and the probability there is 0.5 as well. Statistically speaking, the probability of getting 2 particular outcomes, this and this, is going to be based on a multiplicative function. So in probability and corresponds to multiply. Because the probability of this happening and that happening has to be less than the probability of any of those individual outcomes. And when you're dealing with probabilities or numbers less than 1.0, multiplying them leads to a product that is smaller than either individual. So the probability of getting a tail at time 1 and a tail at time 2 is 0.5 times 0.5, which is 0.25. So the probability of 0 heads, which is a tail both times, is 0.25. So put a little bar right there. Now, what about the probability of getting 1 head? I can get a head at time 1. That has a probability of 0.5. If I get a head at time 1 and I'm getting 1 head total, that means I'm getting a tail at time 2. The probability of this constellation, a head first and then a tail, is 0.5 times 0.5, which is 0.25. But there's another way I could get 1 head, which would be I get a tail first, 0.5, and then I get a head second, 0.5. And the probability of that constellation is also 0.25. Now, here's another little probabilistic rule, which is the word or corresponds to add. Because it's more inclusive, right? There's more ways that I could get 1 head than I could get 0. This constellation could happen, or, right, that's the or, this constellation could happen. If I add those probabilities, 0.25 plus 0.25, I get 0.5. So in probabilities, if I'm adding things together, that means it's this or that. And then finally, this possibility of getting 2 heads, I'd have to get a head at time 1, which is 0.5. I'd have to get a head at time 2, which is 0.5. That means I'd have to get this and this. Remember, and is multiply, so that's 0.25. So this is a probability distribution. Remember, probability distribution is determined by math, right? By like formulas and processes like this. It's not based on actual data. It's different. It looks like a frequency distribution, but it's different because it is not based on actual data. It's based on expected data or predicted data over an infinite amount of time, essentially. So that's a probability distribution. And that's how these things are computed. Like I said, they're computed mathematically. The mother bear of probability distributions is what we call the normal distribution. It's kind of like the boss. There's multiple probability distributions that we will go through in this class, but the one that is in many ways the most important is the normal distribution. Just like the distribution I put up there, the normal distribution is mathematically determined. It's got an x-axis. It has a particular shape to it. I've been teaching this since 1996, so I know what these things look like and how to draw them. A few things about the normal distribution. First off, I always like to draw a line in the middle. The line in the middle represents a few things. Largely, it represents the mean of that distribution. Also, if we think about a probability distribution, the y-axis, if you recall, corresponds to probability. How probable is a particular value of x? The higher the curve is, the more probable that particular value is. The mean in a normal distribution is the statistically most probable value in a distribution of scores. So I always demarcate the mean. The mean is also useful because it tells you the fact that this is symmetrical. So it divides a symmetrical distribution or a symmetrical shape in half. As scores get closer to the mean, the curve gets higher. Those scores become higher in probability. As scores go what we call further toward the tails, you can see this kind of looks like a tail of an animal. This kind of looks like a tail over here. As scores get closer to the tails, they become lower in probability. So those are the basic features of a normal distribution. Just like with that distribution I created a second ago, where the different sections of the probability distribution are known, we know tons about the normal distribution. And as I've said earlier, that z-scores are something that come back regularly throughout this entire class. They're very useful in thinking about the normal distribution. So we can understand a normal distribution partly in terms of z-scores. Okay, right here, I'm gonna put this stuff in terms of z right here. I'm going to put a z of 0 right there. The fact that that is a z of 0, remember z of 0 means that it corresponds to a raw score that is 0 standard deviations from the mean. So a z of 0 means that the raw score is at the mean. So in a normal distribution, a z of 0 is right at the mean. If we go over here, I'm going to put a z of 1, and here I'm going to put a z of negative 1. My dogs can't stop barking. I apologize, kids. So here's a z of 1, here's a z of negative 1. That z of 1 means whatever raw score it corresponds to, and I'm going to give you some raw scores for us to think about in just a little bit, but it means whatever raw score we're thinking of is 1 standard deviation above the mean. And this z of negative 1 corresponds to a similar point in the normal distribution that is 1 standard deviation below the mean. as I said before, that the sections of the distribution are known, we know that approximately 34% of a normal distribution is found between the mean of that distribution and one standard deviation above it. And similarly, we know that approximately 34% of a normal distribution is found between the mean of that distribution and one standard deviation below it. And again, probability distributions have known information. As we move further away from the mean, the curve gets lower. The curve gets lower means we're getting lower in probability. And so over here, I'm going to put a z of 2. Approximately 14% of a normal distribution is between one standard deviation above the mean and two standard deviations above the mean. And since it's symmetrical, about 14% of a normal distribution is found between -1 or one standard deviation below the mean, a z of -1, and a z of -2, meaning two standard deviations below the mean. So sometimes people are curious as to whether a score is, quote, extreme or not. There's not really what we call a hard and fast rule for that, but one way to think about defining an extreme score has to do with the concept of standard deviation. I always tell people that once a score starts to be outside of this sweet spot here, right? So this speckled area here is 68% of the distribution. Once you're a standard deviation above the mean, or a standard deviation or more below the mean, we're starting to talk about a kind of extreme score. We're starting to talk about scores that are relatively atypical. Now, right here, I'm going to put a z of 3. And I'm going to put 2% right here. And over here, I'm going to put a z of -3. And I'm putting 2% right here. 2%. If your score, whatever it is, your ACT score, your SAT score, your score on some test in school, your score on a personality measure, how tall you are, your score at a swim meet on a particular stroke, whatever your score is, if your score is within 2 and 3 standard deviations above the mean, that's a pretty extreme and unlikely score, right? That's in this little 2% bit of the distribution right over here. Similarly, if your score is between 2 and 3 standard deviations below the mean, whatever that variable is, you're talking about a very extremely low score over here. Now, if you're following along and you're adding these numbers up, you will see that the sum of 2 and 14 and 34 and 34 and 14 and 2 is 100. So that's 100%. But here's an interesting tidbit for you. The tails of a normal distribution go on infinitely, and they never hit the x-axis. I think the word is asymptote, something like that, yeah. So they never actually hit the x-axis. Scores that are more than 3 standard deviations above the mean or less than 3 standard deviations below the mean in a real normal distribution are so remarkably rare that it's as if they're impossible. They're not impossible, but they're so unlikely that it's as if they are impossible. The scientific technical term for this section and this section over here is itty bitty. So it's not to say that those scores are impossible, but there is simply an itty bitty percentage of scores that are that extreme in a real normal distribution. We're going to use this fact to our advantage as we advance in inferential statistics. But there are some really useful pieces of information that we can use in just thinking about a normal distribution. So imagine that you have a mean of 2.5, and imagine you have a standard deviation of 0.5. Imagine this is GPA data. Back when I was in college, everyone says this, but back when I was in college, the GPAs were generally lower than they are now. So my GPA of 3.22 from 1992, that was good. Whereas now, I think that's kind of so-so. But back in the day, that was good. So I'm giving you some data. Imagine a population, university population of students, and the mean GPA is 2.5. The standard deviation is 0.5. Okay, so imagine you had this. Imagine that you had x equals 3.0. I'm going to ask you for 3 questions. We can say, what was that z-score? And then we can ask what percentage were above. And then we can ask what percentage below. So imagine someone has a GPA of 3.0, again, in this universe. In this universe where the distribution is normal, the average GPA is 2.5, and the standard deviation is 0.5. So first off, how can we figure out that person's z-score? Well, z equals x minus m divided by standard deviation. That's a formula that we put up as early as chapter 2 or 3. It will continue to be a relevant formula throughout the course. X, meaning a particular raw score, is 3. So 3 minus the mean of 2.5 divided by a standard deviation of 0.5. So the z-score is 1. So if x equals 3, the z-score is 1. And if we think about this as x's, the mean is 2.5. Here's a raw score of 3. The raw score of 3 corresponds to a z-score of 1. I know that because the z formula tells me that if I take the raw score of 3 and put it into the z-score formula, I get a z-score of 1. What that means is that the raw score of 3 is 1 standard deviation above the mean. So it's sitting right here, right defining this extreme upper section over here. Another question I asked is what percentage of scores are above that particular score? Well, if that particular score, look at this, I'm going to use some of these colored markers that our friend Dana has brought. If that particular score is here, then I'm going to shade everything above it with orange. So everything above it is 14% plus 2%, which is 16%, plus this bit, which is how much again? Itty bitty, so don't even worry about it. So the percentage above is 16%. And a final question I asked here is what percentage is below? Before I answer that, I'm going to give a word of caution. I've taught this class since 1996, and I've probably had 100 students over the years ask me, what's the formula for figuring this out? And my answer here is that when we're dealing with these kind of problems, and we will be dealing with these kind of problems for the next several chapters, there's not really a particular formula. There's a bunch of ways that you can arrive at the right answer. So let's take a look at what percentage of people scored below that particular raw score. Okay, here's how I could do it. I could say it's everyone. I can get my purple marker out. I can speckle it with purple. It's everything purple. Everything purple is below that particular raw score. Well, that means it's 34 plus 34 plus 14 plus 2. Okay, which I think that's 84%. But I know that when I teach this class live, I'll always say, raise your hand if you did it differently. And there's always students who raise their hand and say, yeah, I thought about it totally differently, which is fine. Some students might say, well, this entire half below the mean is 50, and then plus this section of 34, 50 plus 34 is 84. And then I'll usually have a student raise his or her hand and say, oh, I did something totally different yet again. So realize that for these kind of problems, A, draw a picture of a new normal distribution every single time, and B, don't expect there to be a magical formula that's going to answer this for you, because there's a variety of ways to come about to the right answers. Okay, there's one more situation that I want to go over regarding this particular chapter. Okay, so here's a case. I'm going to use my GPA, kids. Back in 1992, I graduated from the University of Connecticut, and my GPA was a solid 3.22. It's good enough to get into the University of New Hampshire's PhD program. I got rejected from a bunch of others, but I don't look back and I don't care about that. I met my lovely wife and have the career and so forth I have now. This is what got me there, kids. 3.22. Now, let's think about those same questions that we just asked a minute ago. We can think about what is that as a z-score. We can think about what percentage scored above. And we can think about what percent scored below. Okay, as a z-score, how do we get that as a z-score? We can use the z-score formula. Z equals x minus m divided by standard deviation, which is 3.22, minus the mean is 2.5, divided by standard deviation of 0.5. Let's get out my fancy calculator. I got 1.44, and Dana tells me that is correct. So Z is 1.44. If we take a look at my distribution up here, I don't see a Z of 1.44. we're kind of in uh-oh land right now. And the reason that there's a problem is because this graph gives you only whole numbers, z-scores that are only whole numbers. The real world is a little more complicated than that. So what we're going to do is we're going to go to our textbook. And if you have the hard copy of the textbook, you're kind of in a little bit of trouble because the publisher, love how I'm blaming the publisher kind of messed up that table. But the paperback copy has it correct. And we're going to go to page 325. Page 325 is Appendix A, and this is essentially a normal distribution table. And it has two columns. It has Z and percent mean to Z. Okay, so it has Z and it has percent mean to Z. So when I have a problem like this, I like to draw a brand new normal distribution. Okay, I have the mean marked because I always mark the mean. I also will mark the particular score of interest. So the particular score of interest has a Z of 1.44. Okay, so here is a brand new special normal distribution I'm creating just for this problem. It has the mean demarcated, the z-score of interest is demarcated, and I'm going to hold on to that, and then I'm going to go to the table. The table has z and percent mean to z. So I have a z of 1.44, and so I'm going to look that up. And if I look up a z of 1.44, I see it has a percent mean to z of 42.51. Can we get that? Is that pretty clear? Mm-hmm. Okay, so right there, and I'll write that on the board as well. So z of 1.44 corresponds to a percent mean to z of 42.51%. Okay. That's how we interpret and use this table. And you're going to see in the next chapter, there's a couple other examples that we can do, but that's pretty much how we're going to use this table. Okay, let me tell you a little bit about another way to think about that table. If we have a normal distribution demarcated in sections like this, we can always put it in terms of what I call A, B, and C. Right? We always have the mean demarcated, right there. And we always have this particular score of interest demarcated, right there. That will always put this into three different sections. That percent mean to Z, if you think about what that means, it means it is the percentage of the distribution between the mean and a particular Z of interest. So all those words, it is this section. See, I'm shading section B. The table always gives you section B. That's a simple way to think about it. Whatever side your z-score is on, the table always gives you section B. The table, by the way, only gives you positive numbers. It does not give you negative numbers because the z distribution is symmetrical, so you can assume it's positive or negative. If you have a negative z, it would give you the same percentage because it's symmetrical. Okay, so now with that information, let's go back to the problem. My raw score was 3.22. What percentage of people scored above me? If I look at this distribution, what section, A, B, or C, is above my particular score? And the answer is section C. How do I figure out what section C is? Well, the table told me what section B is. So section B is 42.51%. So that's 42.51%. To figure out section C, what I'm going to do is go 50, right, this entire half for 50%, minus 42.51%. That's going to give me 7.49%. So what percentage of scores are above my particular score? 7.49%. And again, why did I get into PhD programs 100 years ago? Because back then, GPA was cutting off a pretty elite part of the distribution. Not super duper, but good enough. So the next question is, what percentage of the distribution is below that particular score? Let's use a different color for that. Let's get silly and go with pink. So here's a particular score of interest. Everything here in pink is below that particular score of interest. Well, how can we figure out what percentage of that distribution is that pink shaded area? Well, it's everything that's in section A. A is half the distribution, so that's 50. And it's everything in section B, which the table in the back of the book told us is 42.51%. So 50 plus 42.51% equals 92.51%. So everything in pink there is everything below that particular score, which is 92.51% of the distribution. So there's your normal distribution. If you're dealing with z-scores that are whole numbers, we can use these numbers here. If we are dealing with z-scores that are not whole numbers, we are going to refer to the back of the book, just as we did right then. And if you were a little bit uncomfortable with that, I'd say rewind the video and watch that section again and realize that for the next chapter, we are going to be continuing to use that table, and we're going to make it a lot of fun. That's about it. That's been Stats with Glenn.